All right. This talk today is on buffer overflow protection, their implementations and their weaknesses. I'm Peter Silberman. During the summer, I work for IDFense as a security researcher, and during the fall, I try to go to class. And
I'm Richard Johnson. Do you have volume on the mic?
Do you have
I'm Richard Johnson. I'm a senior security engineer at IDFense Lab.
Well, yours isn't working.
Yeah. Can we get some assistance with the mic?
Here, just talk to this one.
Hold on. Yeah.
It's been the bad luck.
All right, we got some volume. A little bit of volume. Is that better? All right, I think that's good. Okay, so I'm Richard Johnson. I'm a senior security engineer with IDFense Labs. Generally, just work on vulnerability research and software analysis. And Peter, go ahead and introduce the.
All right. Whoa. Great. Love mics. The talk today is going to cover what buffer overflow protection is, how it works. Basically, it's going to, it's the software that prevents overflows, execution of code, and could potentially protect you against ODay. For those of us who are experienced in the Linux realm, know of PaX and other things. The new aspect of this is going to be two products that we did research on that attempt to implement PaX-like protection. And so we'll show you those, and we'll do some demos. All right. We're going to talk about compiler-enforced protection first. And we're going to cover StackGuard, StackShield, and ProPolice. And these are all Linux-based compiler protections. They range from canary-like protection to rearranging the layout of the stack. We're going to also talk about Microsoft's .NET protection, which we've know there's been prior research, so we're going to go over that briefly. We're going to then cover the kernel-enforced protection, PaX, StackDefender 1 and 2, which are the Windows-based, and then OverflowGuard. And finally, we'll introduce you to the attack vector test platform, which will allow the user and developers to test how well their software protects against overflows. You'll notice if you're following along online or in the book that there have been some modifications to the slides and stuff, and therefore we ask that you look up here and then look down because you might not see the slide that's in there.
So compiler-enforced protection essentially takes the approach that they're going to modify compiler in process so that you can make direct modifications to the binary that gets generated by that compiler. General concepts is that they want to protect the control data stored on the stack. Essentially, overflows want to redirect the program execution by overflowing a return address or a function pointer that's stored somewhere in memory. What they try to do is either reorder the stack variables so that if a character array overflows, a pointer won't be after it. It'll immediately overflow the canary, and therefore you know that there's been a breach in the integrity of the program flow. And stack canaries take form in 4 different ways. There's a random canary, which is exactly what it's a randomized long 4-byte value that gets compared during the function prologue and gets generated during the prologue, gets compared during the epilogue to make sure that the modification to the stack hasn't occurred during the process of that function. There's also the XOR canary, which essentially is the same thing, only they XOR it with the original return address so that the generated value is comparable, and you can't just assume that the random value. There isn't much more protection provided. These are just different methods. A null canary is based upon the concept that strings are generally terminated by nulls, and if you have nulls in your shellcode and you try to overflow a function which is a string-based function, then you're not going to be able to insert that null very easily. Terminator canaries take that step a little bit further, and they use a combination of return like the actual return character, CR, LF, and nulls as well, to take care of functions like fgets and actual data functions that don't necessarily terminate on nulls. The advantages of using a compiler-enforced approach essentially is that there's no system-wide performance impact. Later on, we'll talk about the kernel-based. Sometimes you have a performance impact due to the fact that x86 processors don't natively support a non-executable paging mechanism. Therefore, they have to emulate that in software. So there's no system-wide performance impact. You can specifically choose which software will be protected. And if there will be a performance impact, it will be isolated to that binary itself. Not only that, but since the compiler is what's generating the binary from source code, it has intimate knowledge in the layout and the structure. It's able to modify values and relocate things in the order that the binary gets generated. Therefore, in that approach, you're able to specifically work out where vulnerabilities may occur and try to prevent those vectors from changing control of the data. Disadvantages of this is, of course, that you have to apply this to every binary. You have to recompile your libraries. You have to compile the source code that you want to protect. That's going to be a problem if you don't have the source code. And therefore, that's one of the major disadvantages of the compiler approach. Also, since, like I said, the intimate knowledge of the binary structure allows you to change the final generation of the executable, but you have to account for every attack vector. In the case of, next time we come out with a new attack vector, like format strings in the past or, methods for overwriting data, they're going to have to, modify their approach to protect your software differently. StackGuard was basically, it was created by Inix and Crispin Cowan, and it pioneered the theory of stack canaries. And essentially, the stack canary is generated during the function prologue, which is the little stub of code that gets executed before every function. And the validation steps occur at the function epilogue, which is essentially the little stub that gets executed every time you return from a function. Originally, the canary was just put adjacent to the return address, so it was put right before the return address. In a buffer overflow, your data goes beyond the buffer that was originally allocated and eventually hits the control data that's on the stack. So they put the canary right before that control data, check it in the epilogue. If it's been overwritten or modified, then they know that there's been a breach in integrity. Latest versions, as the theory has been progressed, the newer versions protect the return address, the frame pointer. Sometimes they even protect function pointers that are stored on the stack to validate that they are pointing to the text section and or non-executable pages. And also, just in the latest version of StackGuard, the canary location has been modified so that depending on the architecture that you're running your program on, the canary location is put in the optimal place so that it doesn't affect, or so that it's more difficult to actually reach and modify. Essentially, if you're able to overwrite the canary when they compare the canary to the saved value, then you can do it either way. So they change the location of it so that it's more difficult to overwrite. After StackGuard was around, then we had the development of StackShield, which currently isn't really supported, but it's interesting nonetheless. Their approach was the concept of a global return stack and a return range check. Essentially, all it is they copy the return address to a safe location, and they're able to, in the case of the return stack, they just copy it back from that known location, overwrite wherever the return address would have been with their already known saved data, and are able to keep integrity that way. With the return range check, you get the added benefit of being able to know that there's been an overwrite because it compares the saved address with the actual value that's in the stack. So with the global return stack, you're not going to be able to know that it occurred because essentially they don't care what that value is. They just copy it out and put it back. And the return range check, they're able to do the comparison and catch in the act of overflow. Also, one other thing is they do check for function pointers, make sure they're pointing into the text section of the binary, which is an added benefit. The latest developments in the software and the compiler world of ProPolice. And although StackGuard claimed that they were going to be integrated into GCC compiler already, it hasn't really occurred. But ProPolice is starting to get integrated in a number of distributions, such as Gen 2 and a couple of others. And in our test results, you will see that they definitely have provided the most complete compiler-based protection. It implements the safe stack model, which rearranges the actual values in the stack so that overwriting pointers after a buffer is theoretically not possible. So generally, in your usual stack layout, you've got your arrays and local variables, and then your return addresses directly afterwards. In the case of a vulnerable code segment like this one, if you were to overflow the car buffer, then the next thing that you would hit was the function pointer. Well, what they do is they rearrange it so that the function pointers are located previous to that buffer so that you would immediately overflow the saved canary value. And they also save the function pointer in a return or in a local variable or register, which essentially makes it much more difficult to overwrite. And I'll turn it back over to Peter so he can cover the Microsoft side.
All right. Like I've said previously, this has been talked about in depth, so we're just going to touch on it and then move on to the more interesting stuff. Microsoft wanted a way initially to try to secure their products out of the box so that their slow patch time would not be affected. However, so this resulted in them adding a buffer overflow protection into the .NET compiler. The .NET compiler is basically a reincarnation of Crispin Cohen's StackGuard, which we just talked about. However, there are some subtle differences. They call the random value pushed on the stack a cookie instead of a canary, and they also store what would be referred to as the canary death handler in writable memory. So we'll see how that plays out. The .NET compiler works like this. It adds a cookie in front of the save DBP and return address. So if the buffer is to overflow, it will overflow the cookie, and on the check will fail and the program will exit. What happens is the check occurs. The cookie is checked against the stored cookie in the data section. If they're not the same, it checks to see if there's a security handler defined. If there is, and the security handler is stored in the data section, it will call the security handler. Otherwise, it will call the unhandled exception filter. Microsoft also, with this release, made modifications to their exception handler. Some of these modifications were the exception handler can't point to the stack, so you can't overwrite the exception handler and point it to your code. Also, the exception handlers are stored in the load directory config section of the executable. So if it's not a registered exception handler, it will not execute. The bypass. Basically, there are a couple ways to bypass the exception handler. One is that if you can get your code onto the heap, you can point the exception handler to the heap and it will still execute. Also, if you can point your exception handler to a registered exception handler and then abuse that exception handler, you're able to get your code executed. And finally, if you have a pointer overwrite, which is specific to different scenarios, you can overwrite the saved cookie, which will make the cookie check pass, and then you can return it to your code, or overwrite the security handler if it's defined and execute your code that way. And those are just a couple ways that, like I said, it's documented, and you can just read up on it.
So those are the different compiler choices, compiler protections that are currently available. Those take the approach of modifying the binary directly. In the kernel-enforced method, essentially a patch is done in the kernel to add protection features such as a non-executable stack or address layout randomization that essentially try to eliminate the effectiveness of an exploit. If you have the non-executable pages, then obviously if you put your data onto the stack and you try to execute it or in the heap, it's not going to execute. You'll throw a page fault. They're able to catch it. Or in the case of old school exploits that still rely on hard-coded addresses, the address randomization is going to take care of that. So essentially it's accomplished through applying access controls to MMU. So I mean that would be the non-executable pages, modifications to your MPROTECT or your other functions that allocate new memory during the process of your execution, and essentially they limit the use of those functions so that you can't change the permissions of a page at a later date if it's already been written to. And of course, the randomization of the process memory, like I said. Essentially, the goal of kernel-enforced protection, according to PaX, is to prevent or contain the introduction and execution of arbitrary code. Generally, the introduction of arbitrary code into a program is not easy to stop because we have vulnerable functions out there that allow you to write beyond the bounds of your buffers. But you know, I mean, if you put that data there and you can't execute it, then essentially it's no big deal. You're just going to crash the program. Also, execution of existing code out of program order. So if you were able to do, for example, a return to libc attack where the code's already in the program itself, you just redirect the program to execute that code out of the original order it was intended. Or execution of existing code in the original program order, but with arbitrary data. For example, if you were to do a memory copy to a pointer that you were able to control, you can then write arbitrary values to anywhere in your memory space. So they try to contain those three different methods of modifying the program flow. The advantages of this is, of course, that you don't have to have source code. Since it's done on a kernel level, it's system-wide. It instantly takes effect on every program that you execute. And you know, it's a blanket application. And not only that, but kernel has control over the MMU, unlike the binary itself. So you're able to, you know, apply those access controls to the different functionality or the different functions that, you know, allocate new pages or try to change permissions, which are all controlled in the kernel itself. Of course, the disadvantages of this is that it's architecture and platform dependent, unlike a patch to GCC, which will apply across the board since it's just modifying the prologue and epilogue functions. In this case, you're going to have to do a lot more work as far as making it work on a Spark architecture as opposed to x86 or, you know, PowerPC, whatever it may be. And also, you'll have a noticeable performance impact dependent on the way that they implement their page protection. For example, with PaX, up until the most recent version with the Linux 2.6 kernel, the PAGEEXEC was much slower than the segmentation logic. And I mean, it just comes down to the amount of emulation that they have to do in software in the kernel to provide that protection layer. So non-executable protection is the most commonly used access control. I mean, obviously, like I said, again, if you're not able to execute that arbitrary code, then the impact is pretty much negated. A non-executable stack it's on a system, well, they refer to it as enforcing proper memory semantics. You know, it's basically a buzzword that says we need to separate the readable and writable pages. So if you're able to write to that page, then you shouldn't be able to execute it later. By default, on x86 architecture, if a page is readable, it's also executable. So essentially, that could be read, separate the writable from executable pages as well. All executable memory, including the stack, heap, and anonymous mappings, must be non-executable. And that just makes sense. That's where your data is going to be stored. And obviously, if that's your data sections, you shouldn't be executing from them. You should just be modifying the values that are going to be plugged into the actual code execution of the text section anyway. And finally, just deny the conversion of executable memory to non-executable memory and vice versa. So, obviously, if you have a page that's been marked non-executable, so it's meant for data storage, you can't later do a return to libc type thing that would unprotect that data so you could execute it later. ASLR, or address space layout randomization, defeats the techniques that rely on static values or offsets into memory that would generally be a pre-known value. So by modifying the layout of the binary, obviously that's going to shift the locations of all the predetermined addresses. So that will effectively reduce the impact of an exploit because it's not going to get to the right values. Also, it just gives you the advantage of it maps the binary mapping and the loader. It will load at a different location than the standard addresses that are predefined in the kernel as well, and further library linking and kernel space execution is also randomized. So we're going to take a look at PaX. PaX is pretty much the definitive kernel patch as far as implementing buffer overflow protection. Just about every effective kernel patch has been based on the work that PaX project has done, and some of them even include PaX as a subset of the features such as GR security. And as we said, it offers the prevention through those two methods, the MMU access controls and the address space randomization. They refer to their non-executable stack protection as no exec. It obviously aims to prevent the execution of arbitrary code. The three features which ultimately are the access controls are The executable semantics are applied to memory pages, meaning that the separation of executable and writable pages. The stack heap, anonymous memory mappings in any section not marked as executable, such as the text section, are marked non-executable by default. You'll notice if you look at your memory mappings today that some pages, for some reason, are just marked executable, even though they're also writable. They fixed that. And then also the ACLs are applied to mmap and mprotect, so that will later prevent the conversion of non-executable pages to executable. They implement their page protection, non-executable protection, in two different ways. One's segmentation-based, the segmentation logic of x86 processors, and then the other one's the paging logic. Essentially, pages are allocated, and their pointers to them are stored in a PDE or PTE, page table entries, and in those entries are permission bits that essentially define, what type of page this is. Is it a kernel page? Is it a userland page? And in the case of memory that's been swapped out, it'll be marked as non-present so that the kernel knows how to handle that when it's referred to from the program. So if a page is marked non-present or another bit is referred to as supervisor level access, a page fault occurs, and then the kernel figures out what it needs to do from there. If, in the case of the page exec logic, what they try to do is mark the pages as non-present or supervisor level access to throw the page fault when it gets referred to, and it's able to compare if the page fault occurred at the same EIP, or the process count of the program, then you know that the page fault occurred on an instruction fetch, because it's trying to execute code from that location that the page fault actually occurred at. If it's data access, you'll still get a page fault, but the EIP will be different from the actual page fault location. Like if you reference a null, if you have like a null pointer dereference, for example, you're going to get a page fault that says, the page fault location was nulls. It was all nulls, if you get an error. Well, in that case, then you know that the program execution, obviously, you didn't just execute an instruction from, 0 in memory. You're obviously going to be executing from some location. So by doing that, they're able to determine if that was, an instruction fetch or a data fetch, and act appropriately. Segmentation logic is something that we usually don't really, we're not very aware of on a day-to-day basis, because modern kernels pretty much make it transparent in the conversion of logical addresses to physical addresses. Essentially, the TLB, translation look-aside buffer, is what determines if the data access is going to be in a code segment or a data segment. And code segment would be the executable segments, obviously, and the data segments would be the ones that store your data. Usually, the entire memory space is mapped on both the DTLB as well as the code segments. So regardless of where you put your memory, the kernel just handles the translation, and it doesn't separate, data values have to always be below this memory address space, or code values always have to be above this segment. But in the logic, essentially, it knows that if you tried to execute from the data segment, then obviously your page fault will occur, and it can handle it from there as well. The mprotect feature of PaX prevents the introduction of new code, executable code actually, into a given task address space. So the objective is to prevent the creation of executable anonymous mappings. So if you bring in a file and you mmap that in, you shouldn't be able to execute the data that's in that file, or creation of executable and writable file mappings, executable read-only mapping, writable except for performance. They have to do relocations on dynamically compiled ELF binaries, so that they can't really apply the same access controls on that level, because you're going to have to be able to relocate that to a different area in memory. And then also, of course, the conversion of non-executable to executable mapping. Every memory mapping has permission attributes in the kernel and the VM flags field, and essentially there's a number of different permission bits, but the ones that we're mostly concerned with are the writable, executable, readable. And in our case, like I said, readable and executable pages are the exact same thing, since there isn't native support for that non-executable bit. Essentially, once you eliminate all the different combinations of may write, may execute bits, they have to narrow it down to these 4, which I mean, it's pretty obvious. It makes sense that it's okay to have may write and write on the same page, but you can't have may execute and write. You know, I mean, that would mean that you could convert that page to executable later after you've written to it. The ASLR component consists of 4 different subcomponents that are listed here: the user stack, kernel stack, the memory mappings, and executable loading. The user stack is randomized upon each exec call. It has to allocate the number of pages and then maps those pages to the process's virtual space. Usually, you can see that the stack is mapped at BFFFFF. Well, what they can do now that it's in the kernel, they can modify that default location every time a binary is executed, and you know, it will shift. You can look at the PaX docs, but there's variable bit shifts, you know, to introduce different levels of entropy at different points in the memory mappings themselves. The kernel stack randomization essentially works on the theory that, or on the actual concept that every time a system call is executed and the context switch occurs, your execution in the kernel space will start at the same memory location because you can't just leave values laying around in the kernel that are going to be there later. So essentially, every time you do that context switch before you return, the memory is cleaned up and your pointer is going to be at the same location. So therefore, they're able to randomize that every single time you do the context switch and shift accordingly. I mean, this prevents, you know, kernel-based exploits that would normally be able to, you know, try to resolve a current address of where that pointer is and then work from there. So it's pretty effective. The mmap protection essentially is able to modify the location of your heap as well. It just does this by adding some additional functionality in the do mmap and adding a random delta value to the base address before searching for free memory. Whenever you try to mmap something, essentially all it does is it looks for the next chunk of unallocated memory that's of an appropriate size for the memory space that you're asking for. And finally, the executable portion of this is kind of interesting because obviously if you're running a binary that wasn't compiled to be position independent, you're going to have some direct references to pointers in the memory itself, like function pointers and whatnot. Well, what it does here is it maps it as usual, but then it also maps another copy of it using the mmap logic that I just discussed. And then it marks the pages of the originally mapped executable as non-executable. What will occur then is that whenever one of those hard-coded values is referred to, page fault handler will see that this is referring to the original mapped binary and do something that they call VMA mirroring. And you can look at the docs there too. It's a little tricky, but essentially what it does is it resolves the fact that they were trying to execute the non-executable copy, resolves where the currently allocated copy of the binary is, and just redirects it back into that. And back to Windows.
All right, Windows. Okay, so we know that Windows is an open source, so it's not all that easy to modify the kernel. So there are a couple products out there, we reviewed 2, that attempt to prevent shellcode execution, I should say. StackDefender 1.10 does not implement no execution stack. So if you overflow a buffer, you can still execute your shellcode. Instead, StackDefender does what a lot of host intrusion prevention systems are doing, and it hooks APIs and applies ACLs to them. And we'll describe what kind of ACLs they apply. StackDefender installs many files, but we're going to talk about the following files on your screen: the kernel NG.fer, MSVC NG.fer, and NTD NG.fer will refer to quite frequently. Moving on. StackDefender.sys hooks the ZW create file and ZW open file to detect kernel32, MSV search, and NTDLL. If it detects these files, it will chop off the last 6 characters and redirect them into the NG.fer files you just saw. Before we can talk about the NG.fer files, we're going to go over how the hook works. A system call works as follows. EAX will contain the function ID, so 64 is going to be moved into EAX. EDX is going to get a pointer to the userland parameters on the stack. Then the interrupt 2E is executed. This is for system call. However, there's also system enter and fast call. The interrupt table, which we'll describe in the next section, acts as a gateway between user mode and kernel mode interaction. When you call 2E, that dispatches the KI system service, which will look up the kernel service descriptor table, which checks the service table base and indexes that by the function ID. So that's basically, in layman terms, it's basically saying it's getting the it's indexing the descriptor table to get the actual function pointer that we need to execute. And this is done a lot, and it's how userland APIs is going to interact with kernel. To hook the system call, basically we set it up so that we don't receive interrupts. We retrieve a pointer to ZW create file, and then a pointer to KE service descriptor table. We then get what KE service descriptor table, we dereference KE service descriptor table, and we also get the function ID by adding 1 to the function pointer. We grab what function address is pointing to at that ID. We store it in the old function, repeat the process, except this time we overwrite that function address with the function we want to receive our hooks. And that's essentially how they're going to hook, how the hook works in StackDefender. The NG.fer files are used by StackDefender to add randomness to system DLLs. It's not ASLR, it's an attempt at it, it's a Windows attempt. Basically what happens is the 3 files are copied, kernel32, ntdll, and msvcert, into their respective ng.fer files. Those files are then rebased and put on the system. So when the redirection occurs in the ZW open and ZW create file, there'll be files to call. Before we can understand how they're going to modify the kernel ng.fer, we first need to understand the export address table. The export address table is a structure in the executable, and basically it's used to store what functions that usually DLL exports to other processes to use. And so we have to understand how get proc address works. So basically, if you want to get the procedure address of, let's say, connect, you have to obtain the export address table in WSOC32. Then you walk the address of names and address of name ordinals simultaneously. So if you find connect and address of name ordinals, you retrieve what address, if you find connect in address of names, you retrieve where address of name ordinals points, and you index address of functions to actually get the entry point to connect. And we'll see how they're going to overwrite this to point to their own code. Kernel ng.fer is the only ng.fer file modified. The other files are just rebased and left alone. What happens is StackDefender is going to modify the relocation section's characteristics to allow them to write and execute code in the relocation section. What happens is they're going to copy function stubs. So they hook create process A. They're going to copy a stub to the relocation section, which takes the same parameters as create process A, except it does different things. Next, they're going to overwrite the export address table function entry point in the kernel ng.fer to point to the relocation section. So when you get proc on kernel ng.fer, you're actually going to receive the relocation section, not the actual text section. These are the following functions that StackDefender is going to hook. As you can see, it's a wide array. And their view is that most shellcode is going to call one of these APIs, and it's going to allow them to detect the shellcode execution. And as we've seen previously, this theory is flawed. The overflow detection algorithm is somewhat similar to other products we've seen. The relocation section, the function stubs, are going to load proxy.dll.dll. I'm just going to call it proxy.dll because that extra DLL throws me off. Proxy.dll exports StackDefender, and StackDefender takes in 4 arguments. The first argument is a static stack address, so it's going to always be ESP plus OC. Argument 2 is where the function was called from. This is the old EIP. Argument 3 is an integer that does not play a vital role in the detection of the overflow. And argument 4 is the stack address of a specific parameter within that API. So for create process A, they're going to push, argument 4 would be the process name it's creating. Proxy.dll overflow detection goes as follows. They have a routine, an internal routine. It's basically an alert API routine. And what this means is if your shellcode is going to load library with WSOC32, then get proc address on connect and bind, then create process with command exe, it hooks those functions. So it's going to compare string values to certain parameters. And if this occurs within X number of milliseconds, it will mark it as an overflow. We didn't see them pick, this routine did not pick up any of our overflows in the attempts. The other routines did. The next routine is they're going to call virtual query on argument 1 and argument 2. And if the member basic information, the memory basic information's member allocation base are equal, it means that the call was made from the stack, and therefore they're going to mark it as an overflow. Next, they have a feature called enforced writable memory regions. Basically, this means they're going to try to detect heap overflows. This is done by calling isBadWritePointer on argument 2. If it's writable memory region, it's going to return 0, and therefore they're going to mark it as an overflow and exit the program. All right, defeating StackDefender. It's pretty trivial to defeat StackDefender. Since they don't prevent shellcode execution, you could essentially write custom shellcode to put the copy itself onto the heap and mark the heap as read-only and then jump to the heap and execute the actual shellcode portion. You can also bypass their hooks by calling higher level functions. So we have a diagram here. Create process A eventually calls ZW create process. Call ZW create process instead of create process A, and they won't pick it up. StackDefender 2.0. It was initially released, and we did not have time to do a full analysis, so I'm just going to give you a brief overview, and then we're going to do a demo on StackDefender 1.10 and 2.0. StackDefender 2.0 was heavily influenced by PaX. This means they moved away from the API ACLs and more towards the no execution heap and stack and stuff. Our initial analysis shows that they hook ZW allocate and ZW protect, basically to enforce the proper memory semantics needed as described in PaX and as previously mentioned. They also hook interrupt OE, which is the page fault handler, and interrupt 2E, which is, as we saw, the system enter. And that's just a basic overview. It's not in depth. We didn't have time. But let's do a demo here. Hopefully the demo gods are with us on this, but no promises. All right, there's a vulnerability. This image is running StackDefender 1.10. There's a vulnerability in StackDefender 1.10. Because they hook ZW create file and ZW open file, they receive the object attributes parameter. They dereference this without checking to make sure it's valid. Because this happens in kernel, it's a local DOS. It'll reboot the computer. Yeah, so let's just see this real quick. And there you go. It's done. You don't need privileges, and it just reboots the computer with no warning. The next vulnerability was actually found when I can't pause the machine, the virtual machine, because the StackDefender 2.0 hooks ZW allocate, and a lot of people think that the performance would be better than setting pages to supervisor. It's horrible, at least in VMware, and we were unable, if you pause it, it doesn't start up again, so we have to reboot from scratch, which is why it might take a minute. But we found the StackDefender 2.0 vulnerability exists in ZW protect virtual memory. They dereferenced the base address without checking it. It was actually found in a remote attempt we were working on a return into libc for RPC decom, and the screen went blue, and that wasn't supposed to happen. It was supposed to execute shellcode. So we made some decisions and realized what happened. So now you can do it locally on a fully patched system, which is what we'll demo here. Basically, we're going to call ZW protect virtual memory with an invalid base address of like 123456778, and it's setting up right now. And you'll see that the screen will go blue, as previously mentioned. And you'll also get to see the performance impact, probably, that hooking the ZW allocate functions has. All right, so StackDefender 2.0 starting up. We're going to call protect 3, which is the virtual protect. And goodbye. So this also, like you saw, it's the same thing, and it's basically just another one. StackDefender was notified of this problem, and they released a patch, we think, without notifying us. So it's on their website. They've got a new version. Whether or not it fixed the problem, we don't know. That we didn't find out until I left for Vegas, and I checked their website and saw a new version. So it might be patched. Moving on. All right. Oh, well, I was supposed to show this slide before I did that. All right. Well, you've seen the vulnerabilities in StackDefender, and I've described them, so we're going to skip this one. Data security software, OverflowGuard 1.4. This is possibly the first third-party application to implement proper page protection like PaX, and we're going to describe how this happens. OverflowGuard is going to hook during setup the interrupt descriptor table entries at OE and O1. OE is the page fault handler, as we previously mentioned. It has to be modified to support all these faults it's going to receive. And O1 is a debug exception. OverflowGuard installs files, but we're only going to talk about overflowguard.sys. What is the interrupt descriptor table? The IDT provides an array of function pointers that act as handlers for userland exceptions and events. An exception would be a page fault, a read to an invalid memory address. An event would be a breakpoint. So that's the differences. The kernel is going to receive this interrupt request and dispatch the correct handler. The dispatch is done by taking the interrupt number and indexing the IDT. We'll describe how this happens. The index is a little more complicated than it sounds. First, we have to overwrite the IDT. To do this, we call the SIDT instruction, store interrupt descriptor table base, into a given register. Then you add the base address to the interrupt ID and multiply that by 8, and you're going to get the address of your exception handler. However, the exception handler is 2 longs. It's not just one address. So you have to overwrite the upper half of the first long with the upper half of the address you want to be the new handler, and the lower half of the second long with the address you want to be the new handler, with your lower half of the address. So when it's called, it's actually put together. The 2 offsets are put together to form the actual address. So that's just a little interesting tidbit there. And moving on. All right. OverflowGuard has a very interesting mechanism. Unlike PaX and setting everything to supervisor, what occurs is OverflowGuard will take the last module loaded, which is could be like add vapi 32 or whatever, and takes the first and last modules loaded. It walks up from the last module loaded, sets all the memory up in that process address range to read only. It walks down and does the same thing, and until it reaches an invalid memory address, it's going to do that. So it's going to cover all your memory mappings, your PEB, TEB, all of that's going to be read only. And the reason they mark it as read only is because if you mark the PEB as supervisor, there are a lot of times that the PEB is read from, and you can't read from in supervisor. So you're going to have a performance, it's going to be a more performance impact. So instead, they're going to mark it as read only. However, as you guys know, when you write to the stack and it's read only, you're in a page fault. So what happens? Well, OverflowGuard is going to compare the old EIP, which is pushed on the stack during the interrupt process, to the physical fault address. So it's going to convert the old EIP to a physical address as well. If these are equal, it was an execution attempt, and it will mark it accordingly and exit. However, if it's not, it performs the data read process, and we'll explain that. Basically, what will happen is OverflowGuard is going to find the memory address. It's then going to mark it as writable, user, and dirty. So it's taking off the supervisor and read only, if it was read only. It's going to perform a dummy read. This dummy read is going to load the address into the DTLB, the Data Translation Look-Aside Buffer. We talked briefly about the TLB, which is the Translation Look-Aside Buffer. That usually stores instruction fetches on addresses and stuff. DTLB is data, so it's a cache so that you don't have to perform an expensive memory walk every time you access data. It's going to load this. It's going to load this new memory address with the new permissions into the DTLB. It's going to then reset those memory permissions, not in the DTLB, but in the actual memory to supervisor, so that it's not executable again. The program will then have access to that memory. It'll be able to read or write to it. The next time that memory is accessed, because it was dirty, it's marked as invalid. The DTLB is cleared, and the process is repeated. So that's how it's going to protect you. And we'll talk about protection it offers. All right. OverflowGuard and other products have not come up with an effective way to get rid of returning to libc exploits. And one was demonstrated by the Insider in, I think it was November of 2003, that actually bypassed StackDefender and OverflowGuard, and it still does. And so that's one way to bypass OverflowGuard. However, your average attempts on overflows are not going to work. Also, because of how OverflowGuard receives the modules, it walks, because of the first and last and how it has to look at the processes, it does not protect third-party applications as of our testing time. And this is a common theme. A lot of third-party applications are not protected. So your IE, your Office, your AIM, your Trillion are not protected. So it offers a really good security for your services, but you're really not getting what you need for your third-party applications, which we haven't seen yet. And I'm going to hand it off to Rich to describe the attack vector test platform.
So we have all this theory out here, you know, the concepts that the people are trying to apply, but it's difficult to get a good grasp of, you know, how effective these different protection layers are. The attack vector test platform, it's a program that emulates the act of overflowing by calling functions which simulate the attack vectors that are normally taken. For example, if you were to overwrite the return address, that's your direct, you know, run-of-the-mill Stack Overflow. That's one of the test cases. Another one would be like, you know, a function pointer overwrite or a long jump pointer, things like that. So John Weilander did some research on similar topics. Peter, what year was that? A few years back. And,
02, I think.
Yeah, 02. And had a basic structure that we took a little bit further. Peter ported it to Windows. We added some more tests. And essentially what this does is it gives us an objective, you know, a view. Here's on the left column, you can see all the different methods that we added to it that would be test cases for your attack vectors. And on the Unix side, here's how it all played out. PaX obviously is by far providing the most secure buffer overflow prevention mechanism. Across the board, it was able to defeat any sort of, you know, rudimentary attempts. What we don't have in here is a return to libc attack, but at a later date, you guys will be able to get our code off the website, and we've added additional tests, so they just didn't make it into the presentation. For the compiler side, you can also see it's very interesting that you know, StackGuard was the first, and it provided protection against 4 different test cases. The green means that it successfully protected against this attack vector. Red, of course, means that it didn't. So, you know, it was able to protect your return address overflows, your old base pointer overflow. Those are just generic stack overflows. The StackShield took it one step further. It was able to provide some additional protection to pointers on the stack as well. And then ProPolice, by far, is providing the best protection from the compiler standpoint, as you can see here as well. And essentially, you know, the Unix portion of our talk was to set up, you know, the developments and the influence that it's taken effect on the Windows world, because, I mean, it seems to be the major interest in our commercial, you know, sector. But as you can see here, I mean, it's just as important to know on the Linux side that what solutions you can be using to protect your systems as well. And I'll let Peter explain the Windows.
All right. I know this looks like a twisted rainbow or something. Our original theory was that we'd have differing results. So we'd be able to show you something like what you saw with the Linux graph. However, as you see with all that black, that was not the case. Black signifies that we do not have that test implemented for Windows. However, if you go to the website, we'll have up a new attack vector with much more implemented. It was a time-constrained thing. We've also added a ASCII return into libc exploit for Windows. Those are very painful to write, as I'll tell you. It's a return into libc, and it'll test Windows return into libc protection. So as you see, Visual Studio.NET protected against everything. However, we didn't have heap overflows implemented at the time, so it didn't do anything for us. OverflowGuard didn't protect anything. As we said, it does not protect third-party applications, and this is an example. We actually tried to, it claims it protects third-party system services. So what I did was there's a tool like serveany offered in the resource kit. I added the test bed and gave it a parameter to try to execute. It still didn't work well. We had mixed varying results. It has to do with load time of how fast OverflowGuard's watching the system service process. So that's what we believe, at least. StackDefender 1.10 did just as well. And the reason that is because we used common shellcode that was released by Matt Miller. We just cut and pasted that because we didn't feel it was right to write shellcode that would, you know, cheat it. We thought that we were trying to gain control of the flow of the program, and that's what we did instead. So if we had custom shellcode, as we said, we could have bypassed it easily. StackDefender 2.0, they say they protect against third-party programs. I talked with them, was unable to replicate this, but it's still possible in this new version. They fixed a bug that was preventing that. So as you can see, they also perform very poorly. And like I said before, there are many more test scenarios, and there's also the return into libc for Windows that's pretty cool. All right, the conclusion. Well, the test results are showing the various coverage that each protection is able to offer. And you can see that from the graph. And the Windows protection, as we can see from the graph, is not advanced yet. All these programs had to disassemble the kernel, disassemble internal structures to get this kind of knowledge. So it's going to take a little longer. There are a few compiler options for Windows, unlike Linux. And that's probably one of the problems. Also, we haven't been able to implement successful protection of third-party applications. And there are probably unseen problems that pop up when you try to do this. However, as we've shown you, a combination of both compiler and kernel-based protection is probably the best method and will offer you a reasonable amount of security. We'd like to thank Matt Miller for technical insight and Lord Yupp for conceptual contributions. We'd also like to thank iDefense Labs, Dr. Jer, whatever. Yeah, we'd just like to thank people. Read the slide if you want to see who we thank.
And thanks for coming, too.
Yeah, thanks for coming. Questions? The question was XP Service Pack 2, buffer overflow protection. That's interesting because I actually started talking to some Microsoft guys, so I'll give you the gist of what I know from them. Basically, they're waiting for hardware support. So if your processor supports NX, and Intel does not have any out right now, only AMD does. So that will be the Service Pack 2. Well, that's what your protection will be. I haven't been able to test it. I'd love to get it going so that I could see how it performs against everything. And like I said, you need that processor. Yeah, it is, as he said that the AMDs are 64-bit, which is also the case. I'm sorry? Okay, they're saying that the new Intel processor will have the Intel bit, but as we showed you, you do not necessarily need hardware support to implement something on Windows that offers a reasonable amount of security. Basically he said that, for those of you who couldn't hear, that 64 bits what's supported, and it's AMD only. That's the gist of it. Any other questions?
Well, I'll address that. Since what we were essentially testing were the attack vectors, it's pretty inconsequential what architecture you're running it on. It's the same theory. It's when you get down to the shellcode level or the implementation of their MMAPs and and different things like that, their mallocs and whatnot. Those will be architecture specific. But the nice thing about this is that we took the approach that just by testing the attack vectors, which essentially is what redirects your program flow in the long run, it applies at a higher level, so it doesn't really, it's not affected. And
I forgot to say, the attack vector is open source, so vendors and users can modify scenarios and add it, and say on my website, hey, it protects this, hey, it doesn't protect this. It's basically a offer.
The only other thing is that there are architectures, of course, that have native, page protection. So, in those cases, of course, it's going to be faster and things like that. But essentially, as far as the attack vector platform, the test results wouldn't be different.
You guys see any problems running like GCC, the ProPolice patch on top of PaX? Are they going to step on each other?
No, I mean they really shouldn't, because essentially the methods of applying the protections are completely independent. The only thing that would be of concern is possibly a performance hit. I mean, you're going to have a little bit of extra code added to the binary and a little bit of extra code added during the kernel processing. So, no. No. Well, I mean, it's pretty apparent when you run a kernel protection that it does have a performance impact. You're executing more code, and there's more instructions being executed, right? I'm sorry?
Can you feel it?
I mean, that's That would be dependent upon their implementation. I mean, I don't have any data on that.
We didn't test that. Thank you guys very much. Oh. It's going to be on Black Hat, and we'll also have it on iDefense. So, thank you.